How to build AI agents. Building AI agents involves combining software engineering with artificial intelligence techniques so that these agents can perceive their environment, reason about their tasks, and take actions, often autonomously, to achieve specific goals. The exact steps will vary depending on the type of agent and the problem you are trying to solve, but here is a high-level guide to help you get started. 1. Define the problem and requirements. Goal. Identify what you want the agent to accomplish, e.g., information retrieval, data analysis, autonomous decision-making, or control of a physical system. Environment. Describe the context or environment in which the agent operates. This could be a simulation, a real-world setting, e.g., robotics, or a purely virtual environment, e.g., an online service. Constraints. Clarify performance requirements, resource constraints, safety requirements, or real-time response needs. A clear understanding of the problem and its constraints helps you choose the right agent architecture, algorithms, and tools. 2. Choose an agent architecture. Several common AI agent architectures exist, depending on the complexity and nature of the problem. Reactive agents. Make decisions based on the current state, observations, without any internal model of the world. Typically faster and simpler, popular in robotics, e.g., subsumption architecture. Model-based agents. Maintain an internal model or state representation of the environment. Better at dealing with partially observable or complex domains. Goal-based and utility-based agents. Plan and act to achieve goals or optimize a utility function, a measure of value. Often used in decision-making systems, planning tasks, and advanced robotics. Learning agents. Continuously learn from their experience, data, interactions, feedback to improve performance over time. Typically use machine learning, supervised, unsupervised, reinforcement learning, etc. 3. Gather and prepare data. Data sources. Identify relevant data for training or for the agent's decision-making process. This might include sensor data, text data, images, or user interactions. Cleaning and labeling. Ensure the data is labeled or prepared properly if you're using supervised learning approaches. Data pipeline. Consider how new data will be collected and integrated over time. 4. Select AI techniques. Depending on the agent's tasks and capabilities, you can combine one or more of the following. Classical AI/symbolic methods. Rule-based systems, logic-based reasoning, knowledge graphs. Useful for applications with clearly defined logical rules. Machine learning, supervised and unsupervised. Classification, regression, clustering, dimensionality reduction. Common libraries, TensorFlow, PyTorch, scikit-learn. Deep learning, neural networks, CNNs, RNNs, transformers for tasks involving vision, speech, natural language processing. Useful when large datasets are available. Reinforcement learning, RL. Agents learn via trial and error in an environment using reward signals. Popular for robotics, game playing, e.g., DeepMind's AlphaGo, OpenAI's GEM. LLM-based agents, generative AI. Use large language models, LLMs, such as GPT or BERT variants for reasoning, communication, or generative capabilities. Often integrated with tool usage, e.g., retrieving information from databases, calling APIs, controlling external systems. 5. Implement the agent logic. Perception module. How the agent collects data from sensors or APIs. Includes pre-processing steps, feature extraction, or direct model inference, e.g., computer vision pipeline. Reasoning/decision module. Planning algorithms, A*, D*, or advanced planners. Utility/goal-based decision-making. Policy learned via RL. Logic-based engines or LLM-based chain of thought. Action module. Interacts with the environment, e.g., controlling motors in robotics, sending requests to web services, responding with text, etc. Ensures that the agent's chosen actions are executed properly. Learning/adaptation module, if applicable. Mechanisms for continuous or periodic retraining and adaptation. Feedback loop from actions to the learning model, especially in RL or online learning scenarios. 6. Test and evaluate. Offline evaluation. Compare performance on a holdout dataset or simulator environment. Metrics can include accuracy, reward achieved, error rates, etc. Simulation testing. Run the agent in a simulation or test environment if possible, common in robotics or strategic decision-making. Evaluate robustness to uncertain or edge case scenarios. Real-world or live testing. Gradual rollout in the production environment. Closely monitor performance, correctness, safety, and user feedback. 7. Deploy and monitor. Deployment. Package your agent in a form suitable for its environment, e.g., containerized service, embedded system firmware, web API. Monitoring. Continuously track relevant metrics, success rate, error rate, resource usage. Maintenance and updates. Gather new data, retrain or refine models, fix bugs, and update the system regularly. 8. Safety, ethics, and reliability. As your AI agent operates autonomously, it's essential to ensure reliable operation, thorough testing, fail-safes, fallback strategies for unexpected inputs or changes in the environment. Address bias. If using ML, watch for biased training data or model outputs. Data privacy and security. Safeguard sensitive information and comply with relevant regulations. Transparency. Provide explanations for decisions if the application domain demands it, e.g., healthcare or finance. 9. Example frameworks and tools. Multi-agent simulation frameworks. Jade, Java. Mesa, Python for research-oriented multi-agent simulations. Reinforcement learning platforms. OpenAI Gym, RLib, Ray. Stable baselines 3 for RL experimentations. Deep learning libraries. TensorFlow, PyTorch for building and training neural networks. Large language model agents. LangChain, Haystack, or custom frameworks that wrap LLMs, e.g., GPT variants. AutoGPT, BabyAGI, or similar open source projects that demonstrate LLM-based autonomous agents. Robotics middleware. ROS, Robot Operating System, for building complex robotic applications with different AI components. Putting it all together. Building an AI agent is a multidisciplinary effort. At a high level, design the agent with a clear goal and environment in mind. Choose the right AI techniques, symbolic, ML, RL, LLM-based, for your use case. Implement perception, decision-making, action execution, and, optionally, continuous learning. Test extensively in controlled environments before real-world deployment. Monitor and maintain the agent once deployed to ensure safe and optimal performance. By following these steps, defining your problem carefully, selecting appropriate methods, and iterating through testing and refinement, you can build AI agents that operate effectively and, ideally, autonomously in their target environment.